Hello everyone, welcome to lecture 2 of module 1. In the last lecture, we were discussing about the different emerging paradigms. We talked about Internet of Things ecosystem, how different interconnected devices and the data flowing through them is actually leading to a huge data explosion, which is commonly known as the big data. We also talked about artificial intelligence revolution and its different applications, which are transforming the world around us. Now, going ahead, we also talked about how basically the memory is organized within your conventional computing systems, such as your CPUs. We saw that, immediately inside your processing core or the core of the processor, you have these fundamental units of memory, which are known as registers. All the registers are fastest, and also their size, physical size is largest. What is basically small? Its memory capacity is small. They're only available in some bytes, right? So these registers are typically made up of more than 20 transistors, and hence their physical area is large. However, their speed is also fastest. Now, immediately close to your processing core, you also have another hierarchical level of memory, which is known as cache memory. We discussed that there are 3 levels of cache: L1 cache, L2 cache, and L3 cache. We saw how L1 and L2 cache are composed of a content addressable memory followed by a SRAM memory array, right? So since these cache memories are made up of SRAM cells, which are themselves 6 transistor. So one SRAM cell is 6 transistor. It's composed of 6 transistors. So its area or physical size is smaller as compared to a register, but also its speed is small as compared to a register. However, in terms of its capacity, its memory capacity is large. You can have some megabytes of cache memory. L3 cache, it's not made up of SRAM. I told that it's made up of embedded DRAM, and nowadays people are trying to make it from STT-MRAM. So that we'll discuss later when we discuss about these emerging memory paradigms. But for now, you just remember that in your conventional systems, it's basically embedded DRAM, which composes your level 3 DRAM. And even in this DRAM hierarchy, L3 is like the largest, but the slowest, and L1 is smallest in terms of your capacity, but it's the fastest. Now, this cache memory as well as register together, since it's embedded inside your core, or since it's present in your motherboard, it's actually called on-chip memory. We have another class of memories which are known as off-chip memory, which starts from DRAM. So DRAM is the next hierarchical level, which is also the main memory of your computing system. So these cache memory, we also discussed that they are used to create local copies of the data available on the main memory, because fetching data from the main memory is actually time consuming, and it's also energy dissipating. Okay, so this off-chip memory or DRAM, we saw that its memory capacity is quite huge. Its memory capacity goes in some gigabytes. However, its speed is slow. Also, its physical size is smaller, because typically this DRAM consists of one transistor along with one capacitor. So its size is basically size of one transistor, because capacitors are in general integrated on top of these transistors. So in terms of their lateral area, it's not considered. Right? After that, we have another level of storage, or next hierarchical level was your hard drive or your flash storage. So we saw that its density is in some gigabytes, like it's in some gigabytes ranging from some 500 gigabytes to some terabytes also. However, its speed is like smaller than your main memory, but cost per bit is very small and its density is pretty high. These devices, these memory devices, starting from your registers to cache to your main memory and these hard drives, since they are updated during the operation of your computer, they are known as online memories. So we have like 4 classifications. First is on-chip memory versus off-chip memory. Second is online memory versus offline storage. So what is your offline memory? So your offline memory or offline storage, that refers to what? That refers to the magnetic tapes or RAIDs which are present in your data centers. So in data center, what happens? These magnetic tapes, which are offline memories, they are just used to copy data, some important data, and then they are kept in some stores or something. Only when they have to be used, those tapes will be brought from the store, and then they'll be connected to your computer and the data will be copied. For instance, your removable or external hard disk, that is also kind of off-chip or offline, that is also kind of off-chip as well as offline storage, right? So this was what we discussed in the last lecture. In this lecture, we will be developing our concepts beyond that. So the disclaimers remain the same even for this lecture. Now, before going to the details of these memories, let us also look at the scaling trends. We have been scaling our CMOS devices and circuits to satisfy something which is called Moore's law. I mean, the scaling trend, it actually follows something which is known as Moore's law. So what exactly this Moore's law tells you? So this Moore's law basically tells you that the number of transistors on a chip, number of active transistors on a chip, it is actually doubling every 18 months. So every 1.5 years, if a processor is developed, then it will have twice as number of transistors as compared to its previous generation processor. That is essentially what the Moore predicted, right? And this was actually a prediction from Gordon Moore, and the companies worked day and night to kind of satisfy this prediction, and they have been able to do so. Why are they even scaling? I mean, why are we even scaling the devices? Because when we scale the devices, what happens? Their physical dimension reduces. It increases their on-state current. Like the transistor on-state current increases, and hence if the on-state current is increasing, then it is able to charge and discharge capacitors very fast. So its speed also improves. So you scale the device, your physical dimensions reduce, your current increases, also your parasitic capacitance reduces, right? Because as your size reduces, capacitance is actually proportional to the area. The area is also reducing. So area reduces, capacitance reduces. So first your current increases, second your capacitance reduces, and hence the time it takes to charge those capacitances, that also reduces. So your speed increases. However, at the same time, what also increases is your static leakage power dissipation. So before I go get into that, let me make my first point that the moment you start scaling your devices, your on current increases, your capacitances reduces, and at the same time, your speed, frequency of speed, that increases. But the dynamic power dissipation reduces. Why dynamic power dissipation reduces? Because dynamic power dissipation is actually proportional to your capacitance and supply voltage. You are scaling the supply voltage, you are also scaling the capacitance. So your dynamic power is actually reducing. However, because now your channel lengths are reducing as you are scaling the devices, the short channel effects, they increase significantly. And once the short channel effects increases, the leakage power dissipation, which is actually your power supply multiplied by the offset leakage current, that increases significantly. So you see here that the switching energy is actually decreasing. So as you reduce your gate length from, let's say, 1 micron to, let's say, 10 nanometer, your switching energy, which is actually your dynamic power energy, this is actually reducing because your capacitance is decreasing as well as your supply voltage is decreasing. However, if you compare this dynamic power with your static power, so for gate length going to 1 micron, your static power is quite low, and hence the static power dissipation is quite low. However, as you are reducing the gate lengths, the static power dissipation increases exponentially, and close to this 20 nanometer gate length, there is a crossover. So beyond the 20 nanometer technology node, what we had is the static power actually started dominating the dynamic power. So earlier everything was done, or earlier the main theme or main goal of VLSI design was to reduce the area, because they thought area is proportional to cost, and when they were decreasing the area, they were also getting these benefits of increased speed and reduced power. However, the moment they hit this crossover point, the static power dissipation actually increased, and now they have to worry about this static power dissipation also, because this is now the dominant component, right? And in this era where power is everything, I mean, nowadays you already have such a miniaturized circuits that main focus of the designers is to reduce this power dissipation, because every consumer wants a handheld device with as large battery backup as possible. And to increase the battery backup, what can be done? We can just reduce or minimize this static power dissipation as low as possible. So in this era which is driven by power or energy, this Moore's law is no longer valid. I mean, Moore's law has already reached its saturation. You will be hearing this from multiple researchers across the world, that Moore's law has hit its saturation. So beyond 2020, you will see that it's almost flat. And that has something to do with this static power dissipation. But the other aspect of that is also your fabrication complexity. As you are scaling these devices, your tools for fabricating them also need to be advanced. However, they have also hit a saturation. So let me not get into details of it, but let me tell you, or let me put forward this new thing which is applicable to this era of energy driven systems or energy driven computing system, which is actually known as Kumi's law. So Kumi's law is something which is more applicable to the present world. It is also similar to Moore's law, but the quantity that it talks about is somewhat different. So what Kumi actually predicted was that the computation power or the computation energy, basically the computation power that your processors are taking when they are being run at their peak frequency, that will also reduce by half with every 1.5 years. So this is Kumi's law. So he actually told that the computations which your processor are performing while taking per unit power or per kilowatt hour of power will actually double every 1.5 years. That is, its energy efficiency will double every 1.5 years. And this is something, since it's built upon energy as one of the fundamental units, so this is more fundamental as compared to Moore's law. So Moore's law will die, but Kumi's law will exist. And this is something which is not taught in the textbooks. I don't know why, but this is more fundamental thing, because in this era when we are surviving or where we are living, energy is more fundamental quantity as compared to area. Now with this fundamental understanding of the scaling, let me talk about how cache memory actually affects CPU performance. We saw that cache memory is actually used for creating local copies of data of the main memory, so that your core processing core doesn't have to every time communicate with the off-chip main memory. And this local copy of the data helps you to achieve very fast speed of operation, right? So this is one way in which cache memory affects CPU performance. That is, it increases its speed. Is there any other way? I mean, does it also affect the CPU's power? This is what we'll discuss in this slide. Before I get into that, let me discuss about an important technique which is used to reduce the static power dissipation. So first of all, let me discuss how exactly this static power dissipation comes into picture. So in your typical CMOS circuits, where you have pull-up network and pull-down network which are complementary to each other, either your pull-up network is turned on or your pull-down network is turned on based on the inputs, right? However, as we discussed that the static power or the offset leakage current is significantly large, what happens? Even your pull-down network exhibits, or even that shows you offset leakage current. So offset leakage current flows through that. So there's a path for current flowing between VDD and ground, which leads to leakage power dissipation. And we discussed that it is quite high for this advanced technology nodes, which we are using right now. And every consumer wants that, there should be a handheld device with infinite battery or with a battery which has got a huge backup. And what actually affects the battery backup? It's this static power dissipation, which actually reduces the battery backup significantly. So to save energy or to operate with within resource constrained environment, what people proposed was the use of power gating transistors. That is what they did. They connected two additional transistors in series with this pull-up and pull-down network. So these sleep transistors, as they are called, were introduced. So PMOS was introduced in series with the pull-up network, NMOS was introduced in series with the pull-down network. So sleep is equals to 0, this circuit runs in the usual mode or the normal mode. But when sleep is equals to 1, then what happens? This pull-up network and pull-down network are disconnected from the power supply and the ground, and therefore leakage power is minimized. There's no path between VDD and ground. Still, I would say there is a path. Because of these sleep transistors, they will also have some finite leakage current. So there is a path, but since these sleep transistors are independent of this circuit, you can actually use transistors with large length. So transistors with large length do not show your short channel effects, and there the leakage is pretty small. Since these transistors with large lengths are in series with pull-up network and pull-down network, effectively the current that flows through this entire circuit is limited by the static leakage or offset leakage of these sleep transistors, which can be made using transistor with large lengths. So this power gating is an effective technique which is used in all the industries nowadays, in all the designs, along with clock gating, to reduce the leakage power dissipation. Now with this introduction to power gating, let me go to the fact that many times you leave your system or you leave your devices, or let's say your mobile phones or your processor or your workstations or laptops in idle state. So what happens during that idle state? So when that idle state period is quite low, I mean when you are talking about short standby time, then what happens? the CPU core goes to sleep state. That is, if this represents your CPU core, then the sleep signal gets on. Once the sleep signal is turned on, power is not delivered to this computing core or your processing core. So with the help of power gating, you kind of shut off the power which is going to the computing core. So you reduce your power dissipation by 3 times. Just by doing this, just by attaching these 2 transistors, you are able to reduce your power reduction. Like you are able to achieve a 3 times power reduction by power gating your computing core when your system is idle. However, even at that time, power is supplied to L2 cache. Why power is supplied to L2 cache? So that once we get back from this standby time to the regular operation, we do not have to again fetch the the data from the main memory, because L2 cache is also volatile memory. Since it's SRAM, so this is volatile. The moment if you power gate even L2 cache, all the data content will be removed. So you like shut off the power, you turn off the power to L2 cache. Since it's volatile memory composed of SRAM, all the content is erased, and then again you'll have to fetch data from the main memory once you go to the regular state. So this is what happens when the standby time is short. But when your standby time is large, then what happens? Even L2 cache is powered off, and in that case, you are able to save 10 times power. However, it comes with a trade-off. What is that trade-off? You would see that whenever you go for a large standby time, your computer goes into the sleep mode. And once it wakes up from the sleep mode or the deep power down state, you see the cursor, it's rotating, right? You see that it takes some time to come out of that. Why that time is taken? Why that is so? Because what it is doing what is happening inside your processor is, it is now, again copying all the contents of cache memory again from the main memory. So L1 cache and L2 cache is refreshed every time you wake up after deep power down state. And that causes a delay and you're rotating of that cursor. So there is an inherent trade-off between power and speed in whenever your CPU goes to standby time, or in general in VLSI also, there is a trade-off between power and speed, which is even visible here. Now, as your circuits are becoming more advanced, the frequency of power gating is increasing. That is, even when your device is not idle, you are not all applications are not using all cores of your processor. So the cores which are not being used, they'll be put to power gating mode. So that is something which is happening nowadays. However, if you look at the contribution of the total CPU power, it's actually leakage power of L2, L3 cache, which is more dominant contribution. So your L2, L3 cache, whenever it is being updated, that takes a large amount of power. Also, whenever it is not being used, it consumes a leakage power, and that leakage power of L2, L3 cache, that has become the dominant contribution because the sizes have increased in this modern era. L2, L3 cache size has increased in this modern era, and the leakage power will definitely increase because they are also using most advanced transistors in their SRAM cell, right? So because of that large leakage of the SRAM cell, actually the leakage power of L2, L3 cache is the dominant contribution to CPU power consumption. And how does that translate to battery life? So our battery life now depends upon L2, L3 cache size. Although we want a huge L2, L3 cache size to increase the speed, but we also, there is a trade-off. So if you use a very large L2, L3 cache, then your battery life also decreases. So this basically shows you that, the cache capacity is increasing significantly each year. And now it's in some MBs, right? It's already 64 MBs for the modern systems. So cache memory not only dictates the system speed, but it also dictates your system power nowadays. So this is how, memory is dominating your CPU. Okay, so with that, let me go to another important concept, which, you won't have encountered before. So I was using memory and storage invariably before this. Now I would discuss about what exactly is memory and what are storage. Are those same quantities? Are those different? The question that I asked you even before in the last lecture. So let us, look at this pyramid of memory. So we discussed different kinds of memories. We discussed on-chip memory, which is comprised of, your registers and cache memory. Then you have off-chip memory, which is your DRAM. Then you have online storage. I mean, all of them is Storage also, you can classify them as online storage and offline storage. So online storage is your hard disk, which is updated along with like while your CPU is working. And then there is this offline storage, which is tertiary disk or magnetic tapes, which are not updated online or which are not updated during the operation of your processor. So as you go down this hierarchy or up the hierarchy, if you consider for memories, the cost per bit of memory cells that actually reduces. However, the speed also reduces significantly. So we talked about registers. They take only one CPU operation to get data from the, to pass the data. Cache memories, they take around 10 CPU cycles or some nanoseconds of time. To get data from DRAM or the main memory, you take some nanoseconds, like 60 nanoseconds. Now, to write or read a data from hard disk, you need at least 5 milliseconds. So, the difference or the order of magnitude difference between them is around 6 orders of magnitude, right? The time it takes to read data from disk, while the time it takes to get data from the DRAM or the main memory. The difference between them or the gap between them is huge. It's 10 per 6 orders of magnitude, right? Also, to get data from tape, it's some seconds. So that is again huge. So in 1980s, you had such kind of architecture. Nowadays, you don't have such architecture. And in 1980s, what people did was, since there was this distinct gap between these devices, which are having I would say which are having small capacity but fast speed, and these devices which are having very slow speed but ultra high capacity, some gigabytes to terabytes. So they kind of divided them based on this, and they called this section as memory. That is, they called this on-chip and off-chip as memory, and they called this online and offline as storage. So they decoupled the two based on their speed and their memory capacity. So what is memory? Memory is basically the entities or the fundamental entities which can store data, where your speed is very high, but your memory capacity is limited. Now, what is your storage? Storage is basically used for data, like storage is basically the entities which can retain data, where the speed is quite low, but the capacity is quite high. Memory capacity is quite high. That is, it's in some terabytes or gigabytes. So this is called memory. This is called storage. And there is a huge gap between memory and storage. Today, the scenario has changed. What has happened today is, there are some memory devices which actually fill this gap. For instance, your SSD or solid state drives that are being used nowadays, they are faster than your hard disk, but slower than your main memory or DRAM. So SSD is something which is actually, filling this gap or reducing the gap between memory and storage, according to the conventional norms. Near future, what you can expect is, there would be this huge class of memories which are known as storage class memories, which are actually, faster as compared to the hard disk, but slower as compared to your DRAM. They are denser as compared to your DRAM, but less dense as compared to hard disk. So the density is actually smaller as compared to hard disk, but the speed is actually faster than hard disk. So a new class of memories known as storage class memories, which combine benefits of storage as well as memory, that is a faster time, a faster speed, as well as a higher density, are emerging, and they are bridging this gap between memory and storage. And what are the candidates for them? The main candidates for the storage class memory are the emerging non-volatile memories, which we would discuss in the next slide. So now, earlier we were discussing about on-chip, off-chip memory. Then we are also calling this online memory and offline memory. But people segregated them as on-chip memory, basically your L1 cache, L2 cache, L3 cache, and your register. Off-chip memory, DRAM. These are memory devices. What are storage devices? Online storage, hard disk. Offline storage, magnetic tapes and RAIDs. And then how do you classify this SCM? SCM is kind of a combination between memory and storage, and hence the name storage class memory, right? So now let us go ahead and look at how these memory devices are kind of segregated or classified. So essentially there are two classes of memory devices. One is volatile memory devices, which lose the data once they are switched off. And then there are non-volatile memories, which kind of retain the data even when the power is not supplied to, right? So let us look at the volatile memory. In volatile memory, we see that there are two classes. One is static memories and one is dynamic memory. So what is static memory? Static memory is something where they are used when the case is such that the data has to be stored for a long time, and typically they use this stable state of multi-stable vibrator or bistable vibrator. Typically you see that these multiplex based latch, these are examples of static memories. So these combine these two latches in a master slave configuration, you'll arrive at a register. So at this point of time, I would also like to discuss the difference between a latch and a register. A latch is a level triggered device. As long as the level is retained, it kind of what should I say? The output data reflects the input data as long as the level is high. If it is a positive latch, the moment the clock goes from high to low, then whatever data was present just before that clock edge, that would be retained there. That is a property of latch. What is a register? Register is an edge triggered device. The data, if it's a positive edge triggered register, the data which is at the D input at the positive, immediately before the positive edge of the register of the clock, that will be copied onto this queue. Now, what is a flip-flop? So as Professor Rabe says, a flip-flop is any device which has two stable states. So that's a distinguishing point between latch, register, and a flip-flop. What is a latch? Latch is a level triggered device. As long as the clock is high or low, it will just, if it's a positive latch, then as long as the clock is high, D is actually reflected at Q. What is a register? What is a register? Register actually acts only at the clock edges. If it's a positive edge triggered register, the moment clock goes from 0 to 1, whatever the data was there before the clock edge on D, that will be sampled to Q, and it will then retain there. What is a flip-flop? Flip-flop is any bistable element which has got two stable states, right? So this distinction, I guess you will understand this and you keep this in your mind. Now this is an example of static latch or static kind of memory. What is a dynamic memory, or when a dynamic memory is required? So whenever you have huge change of data, or the data is not being stored, or you don't store data for a longer time. I mean, applications where data is constantly changing, their dynamic memories are more efficient as compared to static memories. And typically what they use is they store the data in the form of charges on a parasitic capacitor, right? So you have dynamic latches also. This is a static latch, but you also have a dynamic latch, right? So in dynamic latches, basically you have a capacitor, and that capacitor stores the data. So that is segregation between static and dynamic. I mean, why static and dynamic both are required. So static memories are actually important, or static memories are actually efficient when your data is to be stored for a long time, in applications where data is to be stored for a long time. Dynamic memories, they are important when your data is continuously changing with the clock, when you have a clock data which is changing at every clock or frequently changing, right? And since you are actually storing it on a capacitor, which is usually parasitic, the structure is actually simple. The dynamic latch structure is actually very simple. However, whenever you are storing charges on a capacitor, you have these MOSFETs around it, and these MOSFETs, as we discussed earlier, they are having some static leakage current. So they continuously leak those charges from the capacitor as well. Because of that charge leakage from the capacitor, the data information can be lost after a certain period of time. So what people do is they continuously refresh that data. They read that data and they write it again. So that because of that leakage, the data information or the information is not lost. So let us talk about SRAMs now. This was about registers. Let us talk about SRAMs now. So SRAMs typically consist of 6 transistors, where you have these access transistors. The data is stored as the values of charge in these nodes, and this is a cross-coupled inverter pair, which is nothing but a latch. Not a latch, but a flip-flop. We can call it a flip-flop. So it's a cross-coupled inverter pair with 2 access transistors. That is a total of 6 transistors. This is the standard industry SRAM cell, which is 6 transistor. As we shall see as the course progresses, we can have like 70 transistor, 40 transistor SRAM, 70 transistor SRAM, 50 transistor SRAM, going till 16 or 17 transistor SRAM also. But those serve some special applications. But in general, the industry standard is the 6 transistor SRAM cell. This is used typically in L1 cache and L2 cache. However, the problems, first, 6 transistors, therefore its area is large. Second problem, 6 transistors. So you have the static power dissipation, which is very high, coming out of all of these 6 transistors. Next, we have this DRAM. So DRAM is nothing but a dynamic RAM or a 1T 1C cell. So one DRAM cell, this is one SRAM cell. So this cell stores 1 bit of information. So if this is storing 1, this node will store 0. So it's like, both inputs, and it's like both true form and the complement is available in your SRAM, right? However, in your DRAM, only one form is available. So DRAM cell basically is a 1 transistor, 1 capacitor cell. So this is 1 transistor, and you see at the drain of it, you have a capacitor. Now, since this is only 1 transistor cell, it is much smaller in area as compared to this SRAM. However, in DRAMs, what typically happens, it's the capacitor which is non-scalable. So SRAMs, you scale these transistors, the size reduces. In DRAMs, transistor size may reduce significantly according to the logic node, but these capacitors are very difficult to scale. So that is one problem with DRAMs. Also, other problem is charge leakage, and hence you have to kind of provide a refresh you have to refresh the data on the DRAM every 0.1 milliseconds or so. So that refreshing also leads to a huge amount of energy, because every time you have to read the data and then write it again. That is called refresh. You read the data, write it again, so that the data is not lost, information is not lost. And in that refresh process, a lot of energy is going. So that is a problem with DRAM. Now, these are the cases for volatile memory. Let us go to the case of non-volatile memory. So the first, or I would say the most mature or most common form of non-volatile memory is the flash memory, which are basically developed on the concept of storing charges or trapping charges in a floating gate, which is called a flash, conventional flash, or a nitride layer. If you replace this floating gate with a nitride layer, it's called a SONOS. So flash memory typically has a MOSFET where you have, so flash memory typically is a MOSFET with an additional charge storage layer in between your gate and the substrate. So in between your main gate and the channel, you'll either have a floating gate which is made up of polysilicon, or you'll have a ONO layer or oxygen nitrate, like oxygen, SiO2, Si3N4, SiO2 layer, which kind of stores the charge. If it is ONO layer, then it's called SONOS. If it is floating gate, then it's called flash. Essentially what happens, if you apply a huge voltage on this control gate, then some amount of electrons from this channel are actually pulled to this floating gate or this nitride layer. Now, once there are charges on this floating gate or nitride layer or any storage layer in between your control gate and the substrate or the channel, then you know from basic physics, semiconductor physics, that charges in the oxide layer change the threshold voltage of the MOSFET. So this is essentially a MOSFET where you are changing the charges in the gate oxide layer just by modulating the voltage at the control gate. So by doing that, you can have different level of threshold voltages, and threshold voltages basically determine your current in a device, right? So let's say we don't have any charges in this floating gate, then we, like for a particular gate voltage, we measure a current which is high. Now what we have done is we applied a high voltage pulse on the control gate. Some amount of the channel charge have tunneled from this silicon channel through this tunneling oxide, which is SiO2, to this floating gate or silicon nitride layer. And now your silicon nitride layer or this floating gate has some charges. So if there are some charges in your gate oxide, the threshold voltage increases. So if the threshold voltage increases, for the same voltage, for the same gate voltage which you are applying, your current is actually proportional to VGS minus VTH. So effectively your VGS minus VTH is now decreasing, and hence the current decreases. So just by measuring the current at a particular gate voltage, you can find out whether charges are present on this floating gate or not. Or you can, in other words, you can tune the current, or you can tune the threshold voltage of the device just by applying some voltage pulses on this control gate or the main gate of your flash devices. So apart from introducing this floating gate or a silicon nitride layer, this can also be replaced by a polarization like a ferroelectric layer. So nowadays you must be hearing a lot about this ferroelectric memories. It's not a new memory. When we discuss, we'll see that it was present even in 1980s, but only recently, with some with the introduction of some CMOS compatible material, it has gained attention again. So in these polarization change memories, we replace this floating gate or this silicon nitride layer with a ferroelectric memory layer, which can be doped hafnium oxide. So what happens exactly is these ferroelectric materials, they are non-centrosymmetric. What I mean by non-centrosymmetric, in your symmetric structures or in your symmetric molecules or in your symmetric, crystalline structures, effective polarization is zero. Net polarization is zero. There would be some dipoles, but the dipoles pointing up and pointing down, they will kind of cancel out each other, and overall polarization would be zero. But if it is a non-centrosymmetric, if it is a not unsymmetric structure, asymmetric structure, then what happens? It has got a it has got some amount of polarization, inherent polarization, because dipole moments do not cancel each other. Because of that net polarization, there is a charge. So polarization can be effectively thought of as charge. So since there's a charge, inherent charge on this ferroelectric material, you assume that there would be a threshold voltage shift. Now the best part about this ferroelectric material is that they're polycrystalline. And in polycrystalline materials, we know that there are several domains, right? There are these several grains, and all those grains are separated by grain boundaries. So these polycrystalline materials, which these ferroelectric materials are essentially, since they are polycrystalline, each of those grains have polarization pointed in a certain direction, and that is random. So initially it does have some non-zero polarization, but if you apply some pulses to it, then you can actually align the polarization of different domains, of different grain boundaries in a certain direction. So you can essentially change the polarization of this ferroelectric material with the help of electrical pulses, and by that you can change its threshold voltage. I mean, it would be too much too much to comprehend in the first go, but you just think of it like this. So you have a material, you have several of these individual dipoles there. By applying a pulse, you can align these dipoles in certain direction. So when you have not applied a pulse, these dipoles are aligned randomly. You have a net dipole moment, or you have a net charge which is smaller. But once you apply a pulse, you have aligned them in a particular direction so that effective charge or effective polarization has increased. So since the charge has increased in your oxide stack, what you are essentially doing is you are changing the threshold voltage again, and you are essentially encoding some bits there. So information is stored, like if it's a 0, then let's say 0 is high threshold voltage such that less current is flowing. 1 is low threshold voltage such that high current is flowing. Like that you can encode like logic values to it. That is how it's typically done. So these are some of the mature technologies. FE FETs or ferroelectric FETs, these are emerging technologies. I mean, ferroelectric memories were present. They were commercialized even in 1990s, but they use different kinds of stack which were not CMOS compatible. So nowadays people have introduced this doped hafnium oxide, and that is CMOS compatible, and so it can be used in your logic, any of the logic technologies that you have. Even 7 nanometer, 5 nanometer technologies, they can have that kind of capability. So that is why now it has regained interest. It was present even earlier. So now apart from this, which is based on, I would say, charge based or something like that, apart from this, there's another class of non-volatile memory which is based on change in resistance. So here you are essentially sensing the current. You are changing the threshold voltage and sensing the current to determine whether it's logic level 0 or logic level 1, whatever is stored. Just to do that, you are actually sensing the current through the device. Now there is a class of memory where you actually sense the change in the resistance, where you sense the resistance of the device to find out whether it's in logic level 0 or logic level 1, or whether 1 was stored or 0 was stored. So the first memory there is PRAM, or phase change memory as we call it. So what is a phase change memory? Essentially, it is a 2-terminal device. So these were 3. So this is 3-terminal device since it's a MOSFET. This is also 3-terminal device since it's a MOSFET. All these memories which I talk about here, they are 2-terminal devices, right? Here what happens? You have top electrode and a bottom electrode, and then there is this phase change material over here. And at the bottom, there is an insulator. But what you essentially do is you fabricate or you introduce a protrusion of metal or the bottom electrode, which goes to this phase change material. Now, what exactly happens here is we heat this phase change material. Now, how can we heat this phase change material? We do not have a heater inside your chip. What we do is we actually pass a current through this phase change material between bottom electrode and top electrode. So because of this current which is passing through it, Joule heating is created, right? So we apply a short pulse of current to create Joule heating. Now this Joule heating, what it does is it kind of melts this phase change material. Now the best part about phase change material is that it exists in two stable states. One is crystalline state where its resistance is smaller. One is amorphous state where its resistance is large. And when you melt this with the help of this Joule heating, if you quench it fast, that is if your duration of the pulse is very short, if you quench it fast, then what happens? This element or this material doesn't get enough time to grow into the crystalline state. So it remains amorphous. So if you melt this and quench it fast, melt quench is fast, then this portion actually becomes amorphous. And if this portion becomes amorphous, effective resistance between this electrode and this electrode is large. However, if you apply a pulse for a long period of time, this cools slowly and it cools in the crystalline state. Since this portion is in the crystalline state, the resistance between top electrode and bottom electrode, when you measure it, it would be smaller. So just by melting it with the help of Joule heating and again crystallizing it, or I would say quenching it, you are able to achieve two different states. If you are quenching it fast, then you are ending up in amorphous state where the resistance is large. If you are quenching it slowly, then you are ending up in crystalline state where the resistance is small. So this is how a phase change memory works. What are the limitations here? Limitation is, since you are using Joule heating to melt it, kind of current that these require is very large. I did not discuss about the limitation of flash. So flash, the limitation is, first is, since you are kind of extracting charges from this channel via tunneling to this floating gate or silicon nitride, in between you have this tunnel oxide, which is very thin. So the quality of this tunnel oxide, which is an insulator, actually degrades as you are, forcing these electrons to tunnel through it. So something which is an insulator and you are continuously, forcing it to pass currents or electrons through it. So its quality degrades over time. And after 10 power 5 cycles, you are not able, this storage layer or this tunneling oxide layer becomes such poor that you won't be able to even operate it. So it works fine till 10 power 5 cycles of writing. After that, it degrades. And that maximum amount of power, like maximum amount of cycles for which your device works, that is called endurance. That we'll discuss in the later slides, but its endurance is low actually. The amount of cycles for which this device can work properly. Phase change memory, cell currents are very large because you have to melt this phase change material and then allow it to cool. Next in this is magnetic RAM or MRAM. So MRAM basically, dwells or develops upon the spin properties of ferromagnetic materials. So here we are talking about ferroelectric materials when we are talking about FRAM, which show polarization change. Here in MRAMs, they exploit ferromagnetic materials, which show a change in the magnetization. So how exactly is magnetization and spin related? What exactly is magnetization? So just to give you a brief overview, I'll be talking about this. So all these memory devices that I'm talking, they are separate modules in your course. Here I'm just giving, the main point about those devices. I'll be discussing them in very detail when we discuss about those modules. So MRAM, exactly what happens? Let's say how electrons can lead to magnetization, or how exactly electrons can generate magnetic fields. So just think about hydrogen atom, single electron moving around the nucleus. So when an electron is moving around the nucleus, what exactly it's doing? So you can think of an electron moving around the nucleus as a current flowing in a circular fashion, right? So if a current is flowing in a circular fashion, does it create a magnetic field? Yes, it does. Remember from your concepts of class 12, Biot-Savart's law and all those things. You curl your fingers around the direction of the current, you'll get the direction of the magnetic field, right? So you curl your direction, you curl your fingers around the direction of motion of an electron across an atom, you get the sense or direction of the magnetization. If the electrons are moving in the opposite direction, if they're spinning in the opposite direction, the magnetization is in the opposite direction. So that is how spin and magnetization are related. Like this is a very layman definition of how spin and magnetization is related, or how basically electrons lead to like magnetization and all. There's a huge amount of physics involved here, where you have this angular momentum and spin momentum coupling, LS coupling. I'll discuss something about it when we discuss about MRAM, but in lay terms or in layman's term, let me just tell you that whenever electrons are flowing across, whenever electrons are revolving across your nucleus, it's kind of generating a magnetic field, and its direction depends upon the direction in which it is moving at. I mean, clockwise. If it is clockwise, then it will create a downward magnetization. If it is anti-clockwise, it will create a like upward magnetization. So we have ferromagnetic materials which are having these kinds of spins, or these kinds of inherent magnetization, which is non-zero. In regular materials, inherent magnetization is zero, because net magnetization of randomly oriented electrons, this just cancel. But in these ferromagnetic materials, because of this LS coupling, which is very high in these materials, what exactly happens? They have a non-zero magnetization. Now, in MRAMs, what happens is they take a pinned magnet at the bottom, which is having a very high magnetization. Let's say it's, the magnetization is along this direction. Then we have a tunnel oxide, typically a magnesium oxide or something, which is very small. And then we have a soft magnet whose orientation of magnetization can be changed. This is also a magnetic material, but where the magnetization is not very strong. The spin magnet, its magnetization cannot be changed. So what essentially happens in MRAM is, the moment you pass a current through this, electrons flow through the spin magnet. The electrons flowing through the spin magnet are aligned in the same direction as the magnetization of the pin magnet. Now, once these electrons tunnel into this soft magnet, they also align all the electrons of the soft magnet along the same direction. So you can also switch it in the other way. You can also switch this soft magnet in the other direction. There is a phenomenon in magnetization which is called tunnel magnetoresistance ratio. So that simply tells you that if you have a stack like this, if both of these magnets are aligned in the same direction, that is, if the spin of the soft magnet layer and the spin of the spin magnet layer, electrons in this like pin magnet layer and soft magnet layer, if the spin direction is same, then the resistance between these two electrodes, top electrode and bottom electrode, that is low. However, if the pin magnet direction and the soft magnet directions are anti-parallel, then the resistance is high. How much high? That is actually dictated by tunnel magnetoresistance ratio. It's basically resistance of parallel state minus resistance of anti-parallel state divided by resistance of, it's resistance of anti-parallel state minus resistance of parallel state divided by resistance of anti-parallel state into 100. So the problem with MRAM is that, this resistance ratio of parallel state when, the magnetization is parallel versus when the magnetization is non-parallel, when it is anti-parallel, that ratio is very small. The maximum ratio between, resistance of this RAP and RP, or parallel anti-parallel, or I would say the maximum tunnel magnetic resistance ratio that I define is 800%. That is, 8 times. So maximum ratio or maximum ratio of the resistances has been found as only 8. Typical values are 2 to 3. So that is something which is, a disadvantage for this kind of memory. Why that is disadvantage? Because you need to have a large memory window. What I mean by memory window, if you do not have a large difference between these two, then it would be very difficult to sense it. Your sensing peripheral circuitry would have to be modified accordingly. So that is one of the major advantages, major disadvantages of MRAM. However, its endurance is almost infinite. People say that its endurance is very large and its density is also small. So that way, it's one of the major contenders for replacing embedded DRAMs in your cache memory, L3 cache. Now we look at the other case, which is called RRAM or resistive RAM, or I would say OXRAM is also a name for it. So there are different flavors of OXRAM, RRAM, or even memristors. These are also called memristors. So what are the different flavors? So typically you have these OXRAMs and you have these conductive bridge RAMs. So what are these OXRAMs? So in OXRAM, what happens? You have an insulator. It's a MIM structure, metal insulator metal structure, where you have a transition metal oxide over here. So in general, if you have a metal insulator metal, it doesn't work as a memory, right? It acts like a capacitor. But in RRAMs, what we typically do is we have a special process which is called forming. So in forming, what we do is we actually stress this insulator by applying a high voltage or a high current. Once we stress it, what exactly happens is the oxide or the insulator undergoes soft breakdown. So in soft breakdown, what happens? Oxygen vacancies and ions are separated. While the ions go to the electrode, or while the ions are kind of, reservoir, like these electrodes act like ion reservoirs, these vacancies are distributed throughout this stack, throughout this insulator. And the electrons can pass through these oxygen vacancies. So now you have something in between the insulator, which is connecting your top electrode and bottom electrode, through which the current can pass. So essentially your resistance actually reduces. Now the best part about RRAM is that if you apply a positive voltage over here on the top electrode, you can attract some amount of these oxygen vacancies towards this top electrode, and hence you uncover some amount of insulator. So now you have nothing connecting top electrode to bottom electrode, you have an insulator, since these oxygen vacancies have shifted towards the top electrode, so its resistance increases. Now, if you apply a negative voltage, positive voltage will repel these oxygen vacancies, negative voltage will attract these oxygen vacancies. So when you apply negative voltage, oxygen vacancies get attracted towards it, and hence some amount of insulator is uncovered. Now if you apply reverse polarity, let's say apply positive voltage, the oxygen vacancies which were close to the surface, now they'll start going towards this bottom electrode. And again, you'll have a conduction filament of these vacancies connecting the top electrode to bottom electrode. Therefore, the resistance will reduce. So by reversibly, like by applying electrical pulses on the top electrode, if you apply positive pulses, you are kind of reducing the resistance or forcing the device into low resistance state. If you are applying negative voltage on the top electrode, you are actually pulling off these vacancies over here, and you're kind of uncovering these insulator, and hence you are moving the device into high resistance state. So this device can be reversibly switched between low resistance state and high resistance state by applying electrical pulses of different polarities. Similarly, we have this conducting bridge RAM where you have a solid state electrolyte. So this is not an oxide, this is a solid state electrolyte. And you have this metal electrode, which is actually reactive with this solid state electrolyte. So at the interface, there is this redox reaction taking place, which leads to the generation of these metal ions. And these metal ions can drift through this solid state electrolyte. So based on the polarity here, so this doesn't require forming. This is based on redox reaction, this doesn't require forming. And based on the applied pulse polarity on the top electrode, you can force these metal ions to connect your top electrode and bottom electrode, or you can bring them back. You can bring these metal ions back to the active electrode by applying a negative pulse. So here, resistance state is basically defined by the oxygen vacancy, conduction filament, and that conduction filament may be made up of oxygen vacancies if it's a oxide-based RRAM or OXRAM. It can be even metal ion-based conduction filament if it's a solid electrolyte and it's a conductive bridge RAM. The major problem with RRAMs or CBRAM is that this vacancy or this vacancy is something which is configuration of vacancy is not tunable, or I would say it is not something which is controllable. We cannot control with a precision, with a finite precision, that okay, when I apply this voltage, these oxygen vacancies will be aligned in this line itself. We cannot say that. These align randomly. We can be sure that they'll align, but we are not sure how they will align. That is one problem with these RRAMs, and because of that, even when you are applying same voltage to this device every time, so you apply same voltage pulse to these devices every time, you will end up having different vacancy configurations, different conduction filaments. Sometimes the conduction filament thickness will change. Sometimes even the number of conduction filaments will change. Let's say I applied 5 volts one time, and this is a very thick conduction filament. I applied 5 volts again. Then what happens? I may end up having 2 different conduction filaments which are thin. I know for sure that it will switch. It will go to the LRS state. But what exactly will be the inner configuration, that we don't know. And that actually dictates the overall resistance. So resistance is actually variable. Even though it's in the low resistance state, the amount of variation in the resistance is large. So that is one of the major problems with this RRAM or CBRAM, which is hindering their commercial applications. Variability is major problem with the RRAM and CBRAM. So let us now discuss the problems with all resistors or latches, number of transistors. So area is large, speed is high, but area is also high. SRAMs, area is large, static power leakage is large. Also, Noise margins reduce significantly when we are scaling the devices. So that is something that we'll discuss when we talk about SRAM. There's a special module for it, don't worry. DRAM's scalability is difficult because it's very difficult to scale these capacitors. Also, you have to refresh this device every time because it's leaking some amount of charge because of this static leakage. Flash devices, mature technology used everywhere, but endurance is a problem. It can work, or you can program this device only till 10 power 5 times. I mean, you can program this device only 10 power 5 times. MRAM, very promising device, may replace your embedded DRAMs in cache memory. Problem, first, materials, ferromagnetic materials are, most of them are non-CMOS compatible. So that is one problem. Other problem, as I already discussed, that this also requires a somewhat large current density for switching. But yeah, the major problem here is the limited time window, limited resistance window. R1 by Roff, or RAP and RP, they are not very different from each other. So that is one of the major problems. So it requires a very sensitive kind of sensing circuit. Phase change memory, pretty good. You would wonder that this phase change memory is no longer emerging, because in 2010 itself, the N series and E series phones of Nokia were using phase change memories. So it's not something which is emerging, but the main problem with these devices is the large cell current that is required to melt this phase change material and then quench it again. So quenching doesn't require energy; it's only required in melting. So melting is highly energy, draining process. So you need large cell currents. RRAM's major problem is variations. Otherwise, this is one of the most promising candidates for the future memory technology. Now, another good part about these, emerging non-volatile memories based on resistance change is that they are two-terminal devices. All these others like flash, Sonos, ferroelectric FETs, all of them are three-terminal devices. These are two-terminal devices, and their area can be reduced significantly. So these two at least take area comparable to a MOSFET. This actually takes area comparable to 6 MOSFETs, but these, since they are two-terminal devices, their area can be reduced significantly. So let us talk how basically these two-terminal devices are arranged in any system. Whenever designing any memory system, let us look at how these two-terminal devices are arranged.